All right, good morning. Let's continue on the lecture here, okay? 4 more lectures left. Again, just want to repeat, most important 4 more lectures for this course. Let's do a very quick review. We covered, at the end of the last lecture, we covered this so-called fundamental theorem of calculus for vector line integral, more precisely. And what the theory said, basically, if you're going to integrate a vector line integral within certain vector field, and that vector field happened to be a gradient vector field. So this vector field is a very special field. It is produced by the calculation of the gradient of a scalar function f. Then this particular field, if you recall that, this is called a conservative field. Within a conservative field, when you do a vector line integral along certain curve C, we have this theorem, which basically very much like the fundamental theorem of calculus, but it gives us this so-called path independence property. Okay. So that's the fundamental theorem here. Let's take a look at very quickly look at an example. Okay. And by the way, I'll put an announcement. Quiz number 3, we'll have it next week. Okay, so last week of a lecture here during the tutorial section. The format will be exactly the same as the previous one. So there will be a bit, basically warm up, last time warm up before your final exam. Okay, so let's take a look at this example here. We have a vector field f equal to yi hat plus xj hat. This is the vector field, and those red arrows represent the distribution of this vector field. Within this vector field, we have inserted a slice of pizza over here. Okay, consisting of 3 curves, C1, C2, C3. And what we want to do is, let's integrate over this curve C, and C equal to C1 plus C2 plus C3, like this. Okay. So if you're going to calculate this line integral, if you're given this question, most probably your first intuition is probably let's get the parametric equation for C1, C2, C3, right? And then we will do the direct calculation as we did in the first half of the last lecture, plugging all the parametric equation into the function f, and do the derivative, do the dot product, and insert limits, and you can do the vector line integral as usual. Okay. Yeah. However, for this particular one, this vector field f, okay, and happen to be a gradient operation of a scalar function when this small f equal to x times y. Excuse me. Now, you might question, how do you know this f equal to del xy, right? I will show you how do we know that after this example here. Okay. But for now, you could just say, okay, so this vector field comes from the gradient operation of this scalar function xy. And if this is the case, then we can assert that this is a conservative field. Okay. If it is conservative field, then we can use the fundamental theorem of calculus for line integral. So basically means I don't need to calculate I don't need to calculate this line integral, right, as usual. I can simply use the value of this potential function f at the end point minus the value of the potential function f at the beginning point. So if you recall this function, we call it potential function. Okay, so this is the point here. I think in this week's tutorial, you'll have an exercise to go through each segment of the curve by direct calculation. Okay, but I want to show you how to use the fundamental theorem calculus for this one here. Okay, so we have basically 3 points: A, B, and a D. Okay, so that's 3 vertices at here. Okay. Let's find the vertices or coordinates for A, B, D at here. For the A, that's pretty simple. It's 0, 0. It's at origin. And B, okay, as the diagram shows, B is horizontally, so B is 1, 0. Okay, that's B. For the D point, okay, and that's basically on a part of the circle at here. Okay, so that's D at here. And this angle, I think I forgot, it's just put it here, it's 45 degree. Okay, so this piece is 45 degree at here. So D is, so C2 basically at here. So D is on C2, which is x squared plus y squared equal to 1. So that's D there. And if you can plug in the 45 degree into this curve, into the circle at here, so your D will turn out to be basically root 2 over 2 and root 2 over 2. Okay, that's your D point. Okay. Okay, so now I'm going to use the fundamental theorem of calculus now. Integral of C is the same as this piecewise integration. So you integrate C1, C2, C2, C3, and you add them together, you get the total line integral. So for C1, if we're going to use the fundamental theorem of the calculus, this is C1 here. According to the theorem, it's the potential function value at the end point, which is a B, minus potential function value at the initial point, which is at A at here. So that gives us f at B minus f at A. And f function is x times y, right? F function is x times y here. So apparently B is x is 1, 0, so you plug in 1, 0 into x, y, you get 1 times 0 minus 0 times 0, and you get 0. That's so easy, right? That's much easier than plugging all these parametric equations to the line integral. But this only applies when it's a conservative field, okay? And then C2 will be f. Let's look at C2. This is C2 here. End point is D. Starting point is B. So f of a D minus f of a B. We have our D point coordinates x, y over here. Minus 1, 0, so you get 1/2. Before I finish number 3 segments, what do you think this total line integral value will be? 0, right? Because it's a circle, so it comes back to itself. Yes. we use this because we at the beginning we said I didn't show you how you get this, but I just tell you this vector field comes from the gradient operation of this scalar function. How we get this, I will show you next. Yeah, it's good thinking, right? Yeah. So there's a way of how to get this basically. Okay. Maybe I want you to verify. Okay, what is del f? Does it give you back this vector field? Okay. Yeah, it certainly will. So let's calculate the C3. As you probably can imagine, the C3 value, the line integral will be -1/2. Okay. And for C3, the endpoint is A, the starting point is D, and that gives you basically 0 times 0 minus √2 over √2 times √2 over 2, and -1/2. So altogether, you get a 0.0 value for the total vector line integral. Okay. That should be a little bit more. When you write things, I want you to write completely everything. Okay. Yeah. The reason is because in this particular case, more precisely, we're doing this. So the C curve C here is a closed curve. Okay, so more precisely. Okay, so that's fundamental theorem of calculus for line integral. And this is something I mentioned for some vector line integral. If you can identify this is a conservative field, then you can simplify yourself a huge amount of a computation time. Sometimes probably even not doable, okay, if you do the traditional direct calculation way. But only becomes so easy if you apply this theorem here. But I leave that ability to you though. You will not be specific as use this fundamental theorem for line integral to calculate certain things. Okay, so just be vigilant in exam. Okay, so let's do a very quick summary, and then we'll answer a couple questions that probably linger in your mind. You know, why you find that a potential function f equal to xy. How do you find that f equal to xy here? Okay. So the summary right here is basically I want to present this 4 equivalent properties regarding this conservative field. Four equivalent state property basically means whatever the 4 things that we're listing at here, okay, will be equivalent to each other. So when you see 1, it will be same as 2. When you see 2, it will be same as 3. Or when you see 3, same as 1. So that's what it means at here. Okay. The first statement is f is conservative. F is conservative. Okay. And when f is conservative, basically what it means is we have our vector line integral equal to 0 over a closed curve. So that's what one property at here. The second one, okay, this f line integral over any curve C, okay, is path independent. So if you have starting point and end point, and you place any curve between these 2 points, if that vector field is conservative, then according to the theorem, then you get the same value. Okay, that's path independent. Okay. I think in your thermodynamics, you probably have a property also. This is path independent right now, right? Yeah, there's a lot of similar things. And the f, okay, is a gradient field. Okay. What this means is basically this vector field must come from the gradient operation of a certain scalar function. So if it's conservative, then it must have this statement here. If f equal to this, then f must be a conservative. So that's what we mean by equivalent statement or property. And the last one that here, okay, has a little bit actually to do with the differential equation. So if our let's say the vector field is written as M and P, so 3 components, and f happen to be the results of a gradient operation of scalar function, so then we certainly know that M and P, right, and equal to, because gradient of the function f is partial f over partial x, and partial f over partial y, and then partial f over partial z. So that basically implies what M and P, where they are from, right? They are basically the partial derivative of the scalar function f. Or in other words, f equal to fx, and n equal to fy, and p equal to fz. Okay. So now if I calculate the vector line integral, okay, and I think I presented this one very briefly to you, I can just simply insert the f with M and P, and then dot dr. Okay, dr is the parametric equation for the curve C, and parametric equation maybe represents x over t, y over t, and the z over t. So the dr here basically dx, dy, and dz. Okay. So multiply these two things together, you get m dx plus n dy plus p dz. Okay. So that's a general formula basically. Okay. If you have a vector line integral, you can eventually write down a formula like this. Okay. But when we do the calculation, I always actually mention this. You don't have to remember all the formulas, but just use the one that you're most comfortable with. Right? So if M and P is actually a result of the gradient of this vector of this scalar function f, then the M and P at here, right? This M dx plus n dy plus p dz, okay, that basically is fx dx plus fy dy plus fz and dz. Okay, that's basically, if this is the case, then you can replace M and P with the 3 partial derivatives. Okay, and now for this particular, the last expression in here. And this last expression, if you recall that, this is essentially what? The total differential, right? This total differential here. Okay. So the number 4 equivalent statement, basically what it's saying is, okay, you have, if you have any vector field, okay, which has M and P, and you're doing vector line integral, this is what we're doing here, okay, which involve this key piece M dx, N dy, P dz. If f is a conservative field, then this expression can be written into df essentially. So give you a simple example. For example, this particular one. This vector field yi hat xg hat. Okay. So we have, this is a 2D vector field. So f equal to yi hat plus xg hat. So basically, this is your m, this is your n at here, right? And if you plug it into the vector line integral, of course we don't have this term here, so we have m here and n at here. Okay. So now we get basically this vector line integral becomes c, and then y times dx plus x times dy for that vector line integral, right? Yeah. As we just shown, this vector f comes from del f or del xy. Okay, comes from here. So this whole piece at here, okay, is basically integral d what? xy, okay, as we've shown here. Okay, right. One more step here, equal to df or c dxy. That good? Yeah. So that's another equivalent basic statement here. So your individual component, additions of individual component is equivalent to a total differential df at here. Is that good? Yeah. As a matter of fact, this is one type of actually solving differential kind of question. For example, you might say, can you solve y dx plus x dy equal to 0? What's the solution for y dx plus x dy equal to 0? This is a first order actually differential equation. Now, if you're able to identify, look, this guy here is basically what? Basically dxy here, right? And that dxy equal to 0. Then you integrate both sides, you get xy equal to a constant c. That's the solution, right? And this is called, basically called exact differential. Okay, called exact differential here. Okay. That's a very special kind of a differential equation, right? And it's related to the line integral over here. So I want you to basically be comfortable with the four statements. Okay. In particular, the top three one here. Okay? The top three, they are very straightforward. The last ones, I find some students having a little bit trouble sometimes when try to understand this part here. But that's okay. If you're having trouble here, you can just focus on the first three. That's the most important part. Okay. Okay. So that's conservative field here. Okay. And but we have two questions we haven't answered here. So the first question, I think you actually probably wondered. The first question would be, how do you know that this vector field is a conservative field? Right, so that's basically the first question. Or the negative question. How do you know that F is not a conservative field? Right? And the second question is, if you know it's conservative, okay? If F is conservative, if F is conservative according to the equivalent property, then F, you can definitely find F by applying the greetings operation on a scalar function. So then the question here is, if F is conservative, then what is the potential function small f? Or how do we find that potential function small f? Okay. So we need to answer these two questions, okay, and to have a peace of mind, right? And that's basically wrap up with the conservative field. So let's answer the first question in here. So I'll say it differently. How to check if F is conservative? We have a theory at here to guide us in terms of this checking in here. I will not be able to provide a proof for the theorem. That's a little bit too much out of scope for this class. So we'll just look at the theorem and then be able to apply it here. Okay. So the theorem says basically, given a domain that is open and so-called simply connected. I try to actually, when I cover this theorem, I used to be very straightforward with a very simple here, but I think it's good sometimes to be a little bit mathematical. Now, in terms of a domain, basically, when you do integral, you have a to b, that's a domain. Okay? When you do a double integral, you have the region, so that's a domain. Right? When you do a triple integral, you have a solid region D, that's also a domain. That's what we basically domain means. So where the xy or xyz coming from. And open simply connected basically means, let's for example 2D. Okay? This is a simply connected region. Okay? But if you have a hole between, and that actually becomes not a simply connected region. Okay. So anyway, we don't need to dive into the detail. We're engineers, so we leave that to the mathematicians here. But I think it's still good to leave it here. Okay. Yeah. Sometimes rigorous doesn't hurt. And this vector field F. Okay, their components, right? It has either 2 components or 3 components. It depends on the dimensions. Okay. Their components are continuous. Okay. So this is also a very important concept. We often take it for granted. We have a function, it's a continuous function, right? We don't think about it. A lot of functions are not continuous. For example, you have a 1 over x squared plus y squared, so that function is not continuous at 0, 0 points. Okay. So this basically means this function's component needs to be continuous within that domain, okay, that region. And let's list our vector function f, okay, which I was writing down as m n and p. So here's my vector function f. My objective is to check if this vector function is a conservative field or not. So the conclusion to check is very simple actually. Then f is conservative if and only if. So this if and only if is a mathematical meaning, basically necessary and sufficient condition. Only if what? Del cross f equal to 0. Now this is a brand new symbol, you're just saying it here. Okay, del cross f. And we have a different name for it, and I'll tell you very shortly here. Okay. Yeah. So what's del cross f? First of all, let's go back to this del, right? That's a gradient operator. Basically just like a derivative operator. This one is a gradient operator. So del basically itself is an operator. It's actually a linear operator, if you recall that. Okay. So del, you can consider it as a vector. It's like a vector derivative operator. So that's del. And f, of course, is m and p. Okay. And then you do the cross product between these two things here. Right? That's basically what it means. So now we write down what's the del cross f. Okay. It's the formula basically for cross product. Formula cross product. First row, I hat, j hat, k hat. Second row is the element for del. So it's not a real constant or anything, but it does have 3 components here. So they are operators, so you just basically put the operator down and here. So 3 partial derivative operator. Partial over partial x, partial y, and partial over partial z. The last row is m NP. Okay, so that's what del cross F is. And now you will calculate the del cross, the cross product here. It's cross product. You know, we can use the formula for cross product as it is. But only difference here is not like two constants multiply each other. So, for example, when you calculate the determinant of this little 2 by 2 here, so it's this times this minus this times this. So this times this actually means partial n over partial x. This times this means partial m over partial y. Okay. So that's how we're going to apply this formula here. And we end up with partial p over partial y minus partial n over partial z I hat, and then partial m over partial z, partial p, partial x, g hat, and partial n, partial x, partial m, partial y, k hat. Okay, that's the cross. Yes. Yes, I already put a negative into the brackets. Yeah. So the original formula is minus this. Yeah. Good catch. Okay, so this is the cross product del cross F. Then what the theorem basically is saying is calculate this cross product and look at the results of cross product. Is it going to be 0 or not? If it's 0, that means this vector function f is conservative. Right? That's a very simple theorem to apply. Okay. So, and now, just to kind of remind you the journey of our calculus here. Straight d to partial to del, and now we have del cross, right? There's another operation in here, so del cross. And from here, very soon, we have a del dot. Okay? So this is the last basically symbol you will see from this lecture. Okay? And this del cross F and del dot F, okay? Just very quickly, we'll come into much detail later. This one here is called curl, okay? And this one here is called divergent. Actually divergence. Okay. Not a movie. It's yeah. So curl F, divergence F. Okay. So we'll look at detail. This is actually two most useful operations. Okay. Calculation-wise, very simple, but it's the understanding takes a little bit effort. Okay. So then, what does del cross F equal to 0 mean, right? If this equal to 0 means basically each individual component at here give you 0. So partial p over partial y equal to this partial m over partial z equal to this partial n and equal to this. Alright. Good. So let's take a quick look example here. How can we apply this theorem to check a certain vector field conservative or not? Any questions so far? Okay, all good? Yeah. Okay, let's give this following vector field f. Okay, I'm going to use a 2D vector for illustration. Okay, so this is a 2D field, just a special case of the 3D field. Basically, your m, n, and if you want to know p is 0 at here. Okay, so I'm going to apply So basically the question is it conservative? So let's apply this del cross f, which a different name is curl f. Okay. Let's look at this curl f, whether it's 0 or not. So del cross f, okay, I, j, k. You don't have to write every time write this, and if you remember the formula, then that's fine. So m, n, p, and p is 0, so put a 0 over here. Okay, so when p is 0, it's a strict 2D vector. Okay. So basically, two 2D vector cross product give you a perpendicular vector to the xy plane, which is essentially pointing to the z-axis direction. So you will end up with a very simple cross product, which is partial n over partial x minus partial m over partial y, and then k hat. Okay. So that's the formula when you're dealing with just a 2D. So all we need to do is calculate two partial derivatives, partial n over partial x minus partial m over partial y. So what's partial n over partial x? Treat y as a constant. Now this is what I actually by mean, everything we learned before midterm, you're essentially using it for solving the question here. Right? Treating y as a constant, so 6x squared, and then, treating y as a constant, what is it? 12xy, and then 3y squared, and partial m over partial y, treating x as a constant, treating x as a constant, so 12xy, your mind will continue to play trick. Okay. Yes, that's it.
Would you mind going over why the I and j terms don't appear in the drawing?
Yeah, we could explain that through using this general results here, right? So if you do have a p at here, so you have this partial p, see, right? Yeah. But p is 0 right now. Right. So these two partial derivatives don't exist. Right. And m and n, because they are 2D vector fields, so they're not a function of a z. So these two partial derivatives with respect to the z, they're naturally 0. So these two terms, they're 0. Yeah. Good. Okay. So now, apparently there's two the same, so that basically give you 0 k hat. So you end up with a conservative field for this particular one. If you ever use this vector field for a vector line integral, so now you're actually confident. I'm not going to do any vector line integral anymore. I'll just use maybe fundamental theorem of calculus for a vector line integral. But however, the question is, then what is that potential function, right? How do I find that potential function? Okay, so that's the second part of the question here. So basically, f is conservative. Okay. Or f equal to del f. So basically now you're confident saying, so there must be a potential function f, okay, and f is a function two variables, f of x, y, okay, and such that when you calculate the gradient of this vector function, or this potential function, it gives you this vector field. Okay, so that's the logic flow at here, huh? Yeah. So let's find what is this potential function, and how do we find this? Very procedural here, okay? Doesn't matter whether it's a function two variables, function three variables. I just need you to follow the following procedures here, but it does take steps though. Okay? So here's a solution. Okay. So from this condition, this f come from this gradient operation, what we can immediately know is here's the connection between the vector function and the gradient results of the scalar function, right? Yeah. So in other words, your m must be this partial derivative, your n and must be this partial derivative. So if you can imagine, if you have a function 3 variables or 3D vector field, then you're just adding another partial derivative and adding p equal to this, right? If it's a 3D vector fields. Okay, so let's focus on the current example right here. So current example is your m function is 6xy squared minus y cubed. That's our m function. Okay? Okay. And this function equal to this partial derivative, right? So I'll write the partial derivative on the other side here. Okay, so I'll write this partial f or partial x over here. So I don't know what that potential function, scalar function f is yet, but I do know now the partial derivative f over x, okay, should give me this m component, which is already given to you. That make sense? Okay. So now I want you to actually focus on this. If I give you an arbitrary first order derivative, let's say for example df over dx equal to x squared, then how do you get this scalar function f?
Take the integral with respect to x.
Exactly. You take the integral with respect to x. So first step you probably do is you multiply the dx over this side here and then integrate both sides here. Make sense, right? Yeah. And then you get f equal to 1/3 x cubed. Okay, that's first year stuff. Okay. So let's come back to here. I have partial f over partial x equal to this. I'm looking for is the scalar function f, right? Now, if I consider, when you do the partial derivative with respect to x, what happened to the y? Constant. So if I consider y as a constant, what is the difference between this one and this one here? Is there any difference at all, right? No difference. So now what I can consider is I will basically, it's like the operation. I can multiply the partial dx over here. So basically, this is not the rigorous writing here. Okay, you don't have to write this step. Basically, the idea is you move this dx to the other side, okay, to this side here, and then you integrate the both sides here. Does that make sense? Yeah. But when you do the integration at this step, you're treating the y as a constant. Okay. So if you do the integration of this side here, basically what we get, this side is integration of df. You get back to this function f. And this integration here, let's rewrite this integration. 6xy squared minus y cubed, and then dx, right? That's the integration. And when you do this integration, you're treating y as a constant. Remember, huh? Yeah. So what's the results of this integration? Good. Treating y as a constant. So 3x squared, y squared minus xy cubed. Okay? Is that it? plus c. Well, plus c is in this case, right? Yes.
So plus a function of 1.
Excellent, right? You plus a c when it's a single function, single variable here. But here, remember, you're considering y as a constant here. So what you really plus is, I would, instead of call it c here, you should plus a function of y at here. Because what happens is, this is like the antiderivative, right? The derivative of this with respect to the x should give you back what? This part. So when you do the which basically partial derivative, when you do the partial derivative of this results with respect to the x, you should get back to this function. So that's called antiderivative. So that's why we need a constant function y at here. That make sense? Yeah. For Simon question is a little bit tricky. I give you a function three variables. Okay. So if I have a function f is a 3 variables, here there might be x, y, z involved. If the first step is integration with respect to the x, now here, guess what should be now? The function you should be plus a function of y and z. Okay. So that's just one step extension, right? Okay. Let's continue it here. So after this step, you find your potential function, which is this. But this is not good because I have unknown function r of y at here, right? So I need to figure this out. So what do? We make use of the second condition, because we made use of the first condition at here. So we make use of the other condition to figure out the r of y. Okay. So let's use the second condition to figure out this r of y here. Okay. Second condition says partial f over partial y equal to the n component, which is 6x squared y minus 3x y squared. Okay, so this is our second condition. So when you apply this second condition, what it means basically, we already have incomplete results for this potential function f. All I need to do is I need to substitute these results into the partial derivative. Okay. And compare with this given function n at here. So let's take a look at what's the partial derivative f over y. So here's f at here, right? Partial with respect to, you consider x as a constant now. So it's 3x squared, well, that's a 6, right? So you get a 6x squared y, and then minus 3xy squared. That's the partial derivative on the first two terms. And this is r of y, and this is function of just y only. So it's not really a partial derivative anymore. It's basically dr over dy. That's the left side. After you plug in the f into this partial derivative, you will get this. And that equal to the given function n, which is 6x squared y minus 3xy squared. And what's good is you have this all cancel out on both sides, and you end up with just dr over dy equal to 0. Then that basically tells you what is the function of y here. Now that's a constant c, right? This time is constant c. Okay. So now I'm putting back the r over back here. So we get our function f. The potential function is 3x squared y minus a square here, minus xy cubed plus c. So put the c back over here, you get your potential function. So this is basically two steps, right? When you deal with a 2D function. If you have a 3D vector field, then you need one more step. Okay? So you'll practice that in assignments. Okay? Yeah. Just have to follow the procedure. I think it's a very a clear procedure here, but you just have to be very vigilant in terms of which variable you're dealing with, okay, and treating the other variable as a constant. Okay. Last step, it's always a good idea to verify what does this del f give it to you. Okay. Is it really the vector field given in this example? Okay. If you had made no mistakes, then you should. If it doesn't, then verify if there are any mistakes in your calculation. Good? Okay, so that more or less wrap up this conservative field at here. Okay. Any questions so far? Okay. Let's go into a next topic, which is a fairly interesting one in my opinion. Okay. Let's look at the curl and its interpretation. Okay. And I have already showed you what a curl is. So curl basically is del cross f. Okay, that's curl. And how do you calculate the curl? It's the cross product over here, right? Yeah, that's curl. So now you can see, if you're required to calculate the curl, the computation, everybody can do it. Okay? So computation is not a problem. But what exactly is a curl, right? What does it mean? You know, how do we interpret this simple meaning at here? Okay? So I'll show you a couple of examples and then to explain it here. Okay, through an example. Let's say I have a vector field. Okay. So here's a vector field v equal to e to the power negative y squared over 8 I hat. So there's not even j hat, just I hat. So there's only I component for this vector field. And if you calculate del cross v, okay, if you calculate this, you end up with 1 over 4. So you can try yourself. And y and e to the power negative y squared over 8. K hat. If you do that, you get this results here for the cross product. Okay. And I can show you what this vector field looks like. So that's what this field looks like. Okay, so these red arrows here, they represent this vector field. In the middle of the y-axis here, so in the middle when y equals 0, you get the maximum length of the arrow here, and when y goes beyond 0 to the negative infinite or positive infinite, the arrow becomes smaller and smaller. Okay, yeah, makes sense, right? The exponential decay function. Okay. So this one, it should remind you, it's almost as a flowing of what? A river, right? If you observe the water flow in the river, the water tends to flow faster in the center of the river and then slow down as it's close to the bank of the river. Okay. So now if I toss a stick into the river, basically if I'm tossing a stick into a vector field. So what do you think these two sticks will do? They spin, yeah. So for the first, for the top stick, what direction do you think it's going to spin? Counterclockwise. And for the bottom one here, clockwise, right? Okay, this is clockwise. Yeah, yeah. At the same time, the stick, of course, will do a translational motion too, right? Yeah. Yes. The top one here. So you have a bigger force down here, so it rotates this way, right? Yeah. Good. So this actually tells you this particular vector. You look at the vector field; it's all horizontal, right? And actually, in fluid mechanics, we call that shear flow. Okay, and it's all horizontal. However, when you look at an individual point into this vector field, there is this tendency to cause a rotation. That makes sense, right? And that's something we really want to extract out of it. Okay, yeah, the rotation elements of that vector field. Does it cause rotation or not, basically? Okay. How do we extract that information out? It's the curl. Okay, it's this curl operation. So, as you recall, so I'll go a little bit slow here. As you recall here, we have learned vector line integral. So vector line integral, the writing is like that. Okay. We typically use the first formula because that's almost the final results of the formula. But if you remember, this formula actually comes from this one at here, right? So you have a vector field going along certain, let's say, closed curve C, and then the t hats at here represent the unit tangent vector to that curve C, okay? And ds represents basically a small displacement around this curve C. Okay. And this one here, I call it, if you basically consider, this is can consider as a circulation, okay, around C. Okay, circulation around the C. F is a vector field, whatever the field represents. Maybe fluid, maybe velocity, whatever. And that field, right, how much of that field circulate around this curve C can be calculated using this formula, right? So F dot T hat, and you get this, okay? So now let's focus a little bit differently here, okay? And I'm going to draw a curve C in a 3D space like that. Okay. And this time when I draw the curve C at here, okay, if you imagine in the 3D, when we draw a curve, closed curve C, I can draw it like this, I can draw it like this, I can draw it like this, right? What's the difference? Even if the same drawing, the difference is what? It's pointing to different directions, right? So I will use another vector here, let's call it n hat, okay, to represent its orientation for that closed curve C. So the n hat, okay, it's perpendicular to the area, okay, enclosed by curve C. Good. Yeah. So that's curve C, we give it a direction concept now, right? And at the same time, the curve C will definitely enclose a certain amount of a small area. So we call it delta A, okay, is the area enclosed by curve C. And of course, you have your vector field F, okay, exists, okay, in the 3D fields. So now let's get back to the area. So your curve C has a certain area, that's a scalar quantity. But I'm going to give the area as a vector quantity here. So vector quantity basically means the same area and magnitude could pointing this way, or pointing that way, pointing this way, as indicated by the n hat, right? So this del A basically is a vector. Its magnitude is the area, and the direction is the n hat. Right? Any vector has two quantities, direction and magnitude. So this is the current vector, which is the area vector. Okay, that's an interesting vector here. Okay. Okay. So now I'm going to do this now. I will integrate around this curve C. Okay. I will integrate along the curve C here. So maybe coming back to this one here, just to write down another formula. That's the most original formula too, right? F. So T hat ds is represented by a vector, displacement vector ds at here. Okay. So the top one here, you could just write it as a ds here, but anyway, so let's keep, that's fine. Okay. So as we said, this quantity is the circulation around the curve C. Okay? Yeah. Yes. Really good question. Orientation actually is something that we're going to have to pay attention to. So typically, your right-hand rule, right, is what matters here. So in this case, when you curve your hand around this curve C, your thumb direction is that positive n hat direction. Now, which cross this? Curve your hand around the curve C. Counterclockwise. When you view from the top counterclockwise, that's typically your positive direction. Yeah. Good thinking. Yeah. So as a matter of fact, you will see in the surface integral, in the next Stokes theorem, there is an orientation involved here. Yeah. Counterclockwise by default is considered as a positive. Yeah. But sometimes you have a curve C purposely giving as a clockwise, right? So we'll come to that later. Okay. Yeah. Okay. So I'm doing here is the line integral over the curve C, and then I'm going to divide this quantity by the area delta A. Okay, divide this quantity by delta A in here. So what does this division, what does this one give us then? So I want you to compare to the simple one. What's the definition of density, mass density? What divided by what? Mass density?
Mass per unit volume.
Exactly, right? So mass density delta mass over m, so you have a mass per unit volume. Okay? Now look at what we have just did here. We have a circulation around the C here, right? And then divided by an area. Can I consider this as a circulation per unit volume? That's the fair comparison, isn't it, right? So this one here, okay, I can consider it as circulation per unit area. So if the mass per unit volume give you density, then circulation per unit area should give me what? Circulation density, right? So if this one give you mass density, then this one give me the so-called circulation density. Does that make sense? Yeah. So to further this a little bit, and we'll come back to it. When you integrate the mass density over a volume, what do you get? You get the mass. Now if I integrate the circulation density over a certain area, what do I get? I get the total circulation, right? So that's the comparison at here, okay? Yeah. It's a very fundamental actually concept, other than just remember this as the formulas, okay? Okay. So then I'll do the next thing here is this. I'll rewrite this formula here. Okay. This circulation density. So I'm going to rewrite this circulation density formula. Now density is always actually not a a patch idea of over a certain patch. Density should be a concept for a certain point. What's the density at that point, right? So then, but this is not a point. This is a certain small area, isn't it, right? So what do? I'm going to let this delta A go to 0. So do an integral, do a limits at here. Let the delta A go to 0. If I do this, this has become a circulation density at a certain point now, right? So this is basically circulation density at a point. Where's the point? The point is inside the vector field, remember, okay? Yeah. Now this formula, this integration at here, this not integration, this limits at here, okay, turn out to be curl F dot n hat. It turned out to be the curl F dot n hat. It doesn't need a 2 or 3 pages to prove this, but you can look at the lecture notes or textbook for the proof. So the idea is, if you do this integration, you will get this. Is that clear? Okay. So I want you to compare these two at here, okay? Yeah. Get back to the most basic one. What does a vector dot unit vector give it to you? That's right. So curl F, first of all, it's a vector, right? And then you're using this to dot the n hat, which is what direction? That perpendicular direction representing the orientation of the curve C. Okay? So when you use this curl F, dot that n hat, you get the circulation density at that point, in particular with respect to that curve C, which has the orientation n hat. Does that make sense? Yeah? So this is basically the mathematic, purely mathematic what it means. When you use this vector here, this is a vector. Okay, if you calculate the curl F, you get a vector here. And this vector, I don't know what this relative, for example, this you calculate this vector at a certain point, you probably get this curl F at here, right? Yeah. And then your n hat, let's say I have, for example, maybe I have a curve C which has n hats like this. Okay. So curl F pointing probably this way. And then you do the dot product, you get this projection, right? The length, the projection. And this length, the projection at here is equivalent to this circulation density at that point. Okay? That's basically what this means. Is that good? Okay. So get back to the rotational idea, right? Rotational idea. If I place, okay, so here is the a little bit demonstration here. If I have a paddle wheel, okay, and I'm interested in measure the wind velocity, and I want to measure the maximum wind velocity, right? So what do I have to do? I have to hold the paddle wheel and then try to orient the paddle wheel to different directions until I see the paddle wheel start to rotate at the maximum speed. That makes sense, right? But as you're doing this, you probably observe the paddle wheel will rotate at a different speed. There's one direction or one orientation for sure the paddle wheel will what? Will actually not rotate. Does that make sense? Right? So when you have a wind flow, there is this maximum wind speed, and that's a certain direction. Okay? And this paddle wheel, the P vector here, is basically which vector? It's the N vector here. And when you orient it at a different direction, you have this N vector. And only when the N vector is in the same direction as which one? Same direction as this guy here, your paddle wheel will rotate at the maximum speed. Because when these are aligning each other, you get the maximum circulation density. So the circulation density is a concept. If you have a zero circulation density, what does that mean? At that location, you will not be able to cause any rotation. Okay. And the curl F, you look at the curl F right here, it basically gives you the direction. The direction of curl F gives you the direction that's going to have the maximum rotation, okay, or maximum circulation density. Okay. So essentially the curl F is a concept or give you information. What is the rotational information at a certain point? Okay? Will there be any circulation at that point? Okay, or cause any circulation or cause any rotation at that point? Okay. So that basically is what the curl F does here. Right? So if I do a little bit summary in here. So curl F has a magnitude and also has a direction. Okay, there's a direction. So if you look at the formula here, so the magnitude gives you the information of the maximum rotation, the rotational speed or information. And the direction gives you basically which direction, okay, has the maximum rotation. Okay, has the maximum rotation. And I also want you to remember, curl F gives you an idea of the so-called microscopic rotation. It's a point information. Okay, at that particular point, what is this rotational information? There's actually a difference between microscopic rotation and macroscopic. Okay, we'll show you next. So when you have a vector field, when you look at the vector field, it's definitely rotating. Okay, there's something rotating over there. But when you look at individual points, okay, on the inside the vector field, and oftentimes it turns out there's no rotation at the point, which I'll show you shortly. Okay. So anyway, let's take a look at the example first. Okay, we're running a little bit tight in here, but I'll show you an example here. So let's say we have a rotation, very common rotation. So this is the rotation around the z-axis with a constant angular speed omega. Basically, if you place any point, okay, if you place any point inside the field, then there will be a rotation around the z-axis with angular speed of omega. Okay, yeah. So from this vector field, okay, I wanted to derive what is the velocity field. Okay. So V equal to what? I want to derive this quantity out of here. Okay. To derive the velocity field basically means if you draw any lines, okay, reading line here, you pick any point on the line, you have basically a velocity field, right, like that. As it's going a little bit far away from the origin, and you have a higher, basically, linear velocity at that particular point. Right? That's a velocity field. Okay? So as you're going away, at each point you get that. Okay? Velocity field can be derived based on the position vector. So position vector, if I pick any point inside this xy plane, my position vectors are cosine theta and r sine theta. Okay. And basically your theta dot, okay, or d theta over dt equal to omega. Okay. So now let's calculate what is the velocity field. It can be calculated by doing the derivative of this position vector with respect to time. So now we have r, we have theta, so we basically have two variables, and when you do this dr over dt, you can use the chain rule. So we get essentially, and also the other thing is, when you pick a point, right, when you pick a point anywhere inside the field at here, and for that particular point, if you look at the magnitude of the r, is always a constant. So the r dot must be 0. Okay, so the r's length doesn't change. So the derivative r over t will not change. Okay. So you're going to get basically the following results that are here. Okay. If you do a derivative with respect to the time. And theta dot is the omega we're giving it here, constant angular speed. So that gives you omega. Let's move the r into it. So r sine theta I hat, r cosine theta j hat. Okay. And we know r cosine theta is x, r sine theta is y. So that gives you omega negative y I hat plus x j hat. Okay, so there we go. So this is the velocity field, okay, due to the constant rotation. And if you draw all the velocity vector out, you get a cluster of velocity vectors from small to big, kind of rotating around the z-axis. Okay. So now I can calculate the curl. And if you do this calculation, okay, and you're going to get 2 omega k hat. 2 omega k hat at here. So what this is, okay, this is basically saying the circulation at a point. Okay, circulation at a point. This is a microscopic rotation. I think I need to show you this one here. Let me see, where is my, here. Hopefully it works. Yeah. There's a lot on the website. There's called Mass Insight. It has a really good app to demonstrate this thing here. Okay, so this is a field negative yx. That's basically the same field we have derived it here. And if you look at this field, right? Look at if you place a ball inside this field, and that ball will rotate around the z-axis, right? And observe what happened. The ball here by itself is also doing what? Self-rotation, right? So there are two information here. There is a self-rotation, and there's also a macroscopic rotation. That self-rotation information is given by the curl. Okay? So in this particular case, you see your self-rotation is actually twice as much as the macro-rotation speed. So what happens is, what's interesting is, let's see for example, so let me quickly just demonstrate this. If I have a different vector field, okay, here's a different vector field, and you can calculate this cross product or the curl of this vector field. It turned out to be 0, okay, aside from the 0, 0 point, okay, it turned out to 0. So when you have a curl value equal to 0, according to our interpretation, so it's 0 anywhere within this field, right? What does that mean? At that any point inside the field, there should be no what? Circulation or rotation, right? So if I look at this demonstration and here, this is you place the ball in the same vector, not the same, in that vector field, and this vector field apparently is like water rotating around the z-axis, right? That's a macroscopic rotation. But look at this ball here. Is there any self-rotation? There's no self-rotation now, right? Yeah. So that's a difference. When you calculate the curl, it gives you this point information, right? The rotational information at that point. There's a difference between macroscopic and microscopic. So let this sink in is a little bit, as I said, computation is not a big deal. It's the proper interpretation of this one is more important at this stage. Okay? Yeah. I'll see you next time.